My dear students, in the last class we discussed the dihedral groups. Now we have today the last lecture of the permutation is alternating groups. So, we begin with the alternating groups today's lecture. So, one of the most important subgroup of permutation group is the set of all even permutations, and we denote it as a AN. So, we just say that we just take all the permutation which is even, you know that we already know how we can say that the permutation is a transportation is a even number is called the permutation is a even. So, we take a collection of all the even permutation, and that permutation is denoted as a AN, and that AN is a subgroup of this group of Sn. Let An be a pi belong to the Sn, and pi is an even permutation, then the set pi An is a subgroup of Sn. So, if we have to show that this An is a subgroup of Sn, means we have to show that this An is a closed under the composition of a mapping into this An, and clearly first thing is clearly this An is a subset of a Sn, because Sn is a collection of all the permutations, and then An we have to pick the all even permutations. So, An clearly is a subset of An, and then we have to just say that An is clearly is a non-empty, because you know that the identity is always is a identity can be written as a 1 2 1 2 in a 2 transposition. So, that is clearly is a even. So, identity this identity permutation is clearly belongs to the An. So, this means clearly An is a non-empty. Now, we have to show that the composition of all the even permutation is again belongs to the An, and also inverse of this permutation is also belong to. If we have to showing that, then we have to clearly say that this An is a subgroup of this group Sn. So, we know that the clearly I already explained that the identity element E of Sn is an even permutation. So, since Sn is a finite, so we need only show that An is a closed under the composition of a function. So, just like I just said that E can be written as a 2 composition even. So, identity is a even. So, this means this E is the element of a An. So, An is clearly is non-empty. Now, we have to show that let the pi and theta are the 2 permutations, even permutation, that means is belongs to An. Then we can write theta and pi as a product of a even permutation, even number of transposition. So, we can write theta as a form of a theta 1 theta 2 up to theta pi 1 pi 2 up to pi 2r, and theta can be written as a theta 1 theta 2 up to theta 2s. If we write the product of these, you know that if we write the composition of these two, then we can write this pi composition theta, this can be written as a pi 1 pi 2 up to pi of a 2r, and then we have a theta 1 theta 2 up to theta of a 2s. And now we know that this can be written as a, this is a total is equal to, you have a this and this is equal to 2r plus 2s, and this can be written as a 2 times of a r plus s, and then you have a 2 times of a r plus s. So, this means again you have to just say that r plus is a even number of a transposition. So, theta and pi composition is also is an even number of a transposition. So, if this is the element of a this is clearly element of An, then we can say that this is pi and theta also the element of a An. So, this means this clearly we say that this is a closed under the operation of a composition. So, just write into this form, and then theta pi as a product of a this is equal to 2r, and this is equal to, you have a 2s. So, this is equal to 2r and 2s, and 2r plus 2s transposition, and then 2r and 2s, 2r plus 2s transposition is again is a even number of a transposition. Therefore, theta pi belongs to pi and theta are the element of a even belongs to an. So this is whole thing is belongs to the an, and that means we can say that the theta pi and theta is also the element of an. That means we can say that this is closed under the composition of functions. So we have to show that, because the Sn is a finite set, so it is enough to show that only the compositions are closed under this composition. This An is a closed, so clearly An is non-empty and closed. So this is clearly An is a subgroup of a permutation group of n symbols Sn. So the group of even permutation of n symbols denoted by an is called the alternating group of a degree n. So now you can simply say that we show that an is a clearly an is a subgroup of Sn. Then the group of a even permutation of n symbols an is called the alternating group of a degree n. So the symmetric group S2, you know the S2 there is a two element E and identity and A, and then containing the factorial 2 there is a two elements where E is equal to, then A is equal to 1 2. Now clearly S2 is an abelian group. Now we take a subset of this A2 is clearly we have a only the identity element. So A2 is equal to, we have a even, because this is a length is equal to this is a odd. So we take any subset which is A2. So A2 is only possibility we have a identity is a even permutation. So clearly A2 is an identity and again is a abelian group. So this means we can simply say that if you see and we have to consider in the another example for we have just check this consider the S3, and then S3 is the element of a like this. S3 is equal to E rho pi gamma theta delta, where I just mentioning the all of them E is equal to, because when we define the symmetric group we use the same notation. So we have to continue the same notation, and identity element, then total number of element of this S3, you know that Sn, order of Sn is equal to simply is equal to factorial n. So this is, you have a S3, so S3 is equal to, you have a factorial 3 is equal to 6. So total 6 elements are there. This is are the 6 elements. And now identity element is equal to this, and then we have a row is equal to, we have to we simplify this. So we just a row is equal to, we write it a 1 2 3 2 3 1, and then we have a we have to write into this form is equal to zeta is equal to 1 2 3, and then we have a 3 1 2, and then we have a this element we write in the form of pi. So pi can be written in the form of a 1 2 3 2 1, and then similarly all others we have to write in this way. Now you see this is a clearly is a even, and this is a odd, and this is a order is this is equal to 3. If is order is m order, then m minus 1 transposition. So this there is a even number of transposition. This transposition is can be written as a 1 3 and 1 2, and this is again, though this is even, and this is odd, this is odd, and this is again we have a order of this is permutation is equal to 3. So if order is equal to this is equal to 3, then we can say that this again is a even. This can be also written as a 1 2 and 1 3, there is a 2. So there are even permutations, we can say simply is equal to we have a these are the 3 are the even permutation in this case. So we have a just this here rho and zeta. So this means we have a A3 is only identity E rho and zeta. Now you just take a square of a row. So if we calculate the row square, row is equal to, you have a so you have a 1 2 3, then 1, 2, 3, 1 goes to 2 and then 2 goes to 3, then we have a 2 goes to 3 and 3 goes to 1, then we have a 3, we have 1, 1 goes to 2 and 2 goes, 3 goes to 1 and we have to just say that 1 goes to 2. So, this then now if you see this one, rho square is equal to, you have a simply is equal to 1, 3, 2. So, clearly this is a zeta. So, this A3 can be written in the form of a E rho and rho square. So, the element of a A3 are the E rho and rho square. We note that S3 consists of the identity which is even, 3 transposition of a transposition which are odd, and the 2 3 cycle which are even, that is I just already explained you. So, this means these are the even and these 3 are the odd. So, we can say that simply clearly zeta is equal to rho inverse and rho inverse is equal to rho square. So, the alternating group AN is equal to, you have this thing, and this is equal to rho. And now clearly if you take this is simply say that if you take a rho to the power 3. So, you have a 1, 2, 3 and then we clearly if you have this rho square is equal to, you have a 1, 3, 2 and then if you take a 1, 2, 3 then you have a 1 goes to 2 and 2 goes to 1 and 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 3 and then again you have a identity. So, that is clearly we have a root to the power 3 is equal to identity. So, this means if we have to this whole group A3 can be generated by this rho. So, with the rho we can generate the rho square root to the power 3 is equal to identity. So, order of 3 is equal to identity, that means we can say that this A3 is a cyclic group. So, A3 is a cyclic group and all the cyclic group and it is an abelian. So, clearly we can say that this group is A3. Initially S3 is not an abelian group, S3 is a non-abelian group, but we find a subgroup and that subgroup is a cyclic subgroup and this cyclic subgroup, and S3 is also not a cyclic. So, because S3 is a non-abelian, so clearly A3 is the cyclic and also is an abelian group. So, clearly we have to show that this alternating group, and now you see if we have a S3 has a 6 element and then any subgroup of this even number of permutations, and so is giving you the 3 elements. So, this means we have to prove a theorem if any permutation S is a number of even and odd permutation are the same. So, that means we have a 3. So, clearly so we have to show that this is one of the example, and the previous class we have to discuss about the S4 the square of a this and then dihedral group of a D4. So, similarly we have to write a S4. S4 is consists the identity is even, and now you have a 6 transposition of a odd and 8 3 cycles they are even, and then we have a 4 cycles are 6 are the 4 cycles, so they are odd, and 3 elements that the product of a 2 disjoint transposition and that is a even. So, that means we have a like this, we have a correction of the even. So, this means even is identity is even, you have a 1 and 6 transposition is odd. So, that means 8 are the this is a 3 cycles. So, we have the 3 cycles is equal to 1, 2, 3, 4, 5, 6, 7 and 8. These are the 8 of 3 cycles. Now, we have a this is equal to odd. Now, we have a 2 are the 2 disjoint transpositions. So, this is equal to 1 and that's product of this, and then we have a this and this. So, this means we have to just write into this. This is clearly this is this even, this even, this even. So, 3 elements that the product of a. So, this is 1, this is 2 and 3. So, this means we can say that simply is equal to there is a total number of 12 elements in this A4. So, these are the in general we can write the transposition of this thing. So, just if you want, you can just verify this clearly. So, we just check this all the S4 consists of the subgroup A4 as again, because A4 is a subset of a S4 and this is a subgroup of a this. And now clearly you just in general we can say that if we have to just say that if we have take a S2, we take a subgroup A2 is equal to this identity element. If we have a S3, then we have a order of a number of element in the A3, we have a 3, and if we have a S4, you know that the order of S4 is equal to factorial 4, then is equal to 24, and then you have a A4, then number of element of this A4 is clearly is equal to you have a 12 something. So, in generally we can say that if you see this is clearly there is a 2 element and then number of even permutation is a 1, S3 is equal to 6 element and then the order of this is equal to 3. So, generally we can say that order of A3 is equal to 3, order of A4 is equal to we have a 12, and then what we just said that in general we can say that order of An has a factorial n by 2 elements are there. Now, we have to just going to prove this result, then the alternating group has the order of alternating group is a factorial n by 2. So, for n greater than A has an order factorial n by 2. So, we go to prove this for each odd permutation pi, the permutation 1, 2, pi is even. If we have a odd permutation and we have to adding one more transposition of a, so this is odd is even. So, 1, 2 into pi is even, and in general 1, 2 pi is not equal to 1, 2 is equal to theta whenever pi and theta are different. So, if we take generally we can say that if we have a 2 permutations, for example we have just take a 1, 2, 3, 4 and 1, 3, 2, 4. So, if we take a 1, 2, 3, 4 and 1, 2 another we can write in this form. So, clearly if we have a 1, 2 pi and whenever theta pi or theta, if we have a pi or theta are the two different permutations, then there is no need to be these two are the same, because 1, 2 and we have to write if we have a pi is equal to we take a 3, 4 and theta is equal to we take a 3, 5, and in generally we just write. So, this is theta and pi are different, then 1, 2, 3 we have a 1, 2, 3, 4 and that is equal to can be right in this is equal to we have 1 goes to 1. So, 1 goes to 2 and then 2 goes to 2, 2 goes to 1. So, this is this 3 goes to 3 again this is the same way, and this again is we have a getting to the, because this is a disjoint and these two are not the same whenever theta and pi are the different. So, clearly for each odd permutation pi, the permutation if a transposition into this pi is even, and also if we take a two different odd permutation theta and phi are different, then this also different. So, thus there are at least as many even permutation as there are odd one. So, we can simply say that there are as many even permutations as the odd ones is there. So, clearly we can say that. Now, conversely for each even permutation pi, the permutation 1 to pi is odd. If we have take a pi is equal to even, if a even permutation, then we take a 1, 2 is a transposition, then clearly even into odd is equal to odd. So, this is giving you odd permutation, and again we have a 1 to pi is not equal to 1 to theta whenever pi and theta are different. So, we can simply say that if these are two different, then simply is this form. So, thus there are at least as many odd permutation as there are even ones. So, we have to show that as many as even permutation as there are odd ones, as many as odd permutation as there are even ones. Therefore, the number of even permutation is equal to the number of odd permutation. So, we have to show that if any permutation group, the number of a even permutation is the same as a number of a odd permutation, and since we know that order of Sn is equal to factorial n, so it follows that in alternating group as a order is factorial n by 2, because order of An is nothing but is equal to collection of all the even permutation. In Sn we have to just say that number of even and odd permutation are the same. So, same number of even permutations, same number of odd permutations, then we have to clearly the order of An is equal to factorial n by 2. So, in generally we have to show that that order of this by the examples. You just say that I take S2, then order of S2 is equal to, you have a factorial 2, and then A2 you have a order of A2 is equal to factorial 2 by 2 is equal to 1, and then we have A2 is equal to, we have identity. Similarly, order of you have to just check order of S3, and now order of S3 is equal to factorial 3, and that is equal to 6, and then we check order of a 3 is we have to factorial 3 by 2 is equal to 6 by 2 is equal to 3, and then we already show that this is a A3 are the element of the A row and row square, and that is the order of a 3. Similarly, for a S4 we have to find that. In general we can say that any alternating group, the order of alternative group is factorial n by 2. So, now I have another result. We just say that whenever n is greater than or equal to 3, the alternating group is generated by 3 cycles. So, An is generated by 3 cycles. So, if you take A3 and then you know that A3 is generated by this is E row and row square, and row is equal to, you have a 1, 2, 3, and that is a 3 cycles is there. So, we just say that in general An is generated by a 3 cycles. If we have all the 3 cycles are even permutations, so that is why we can say that in this form. So, all 3 cycles belongs to the An since they are even permutation. We know that all the 3 cycles A, B, C. So, this is A, B, C, all this type of 3 cycles are there, and these 3 cycles can be written as a AC and AB, and all the 3 cycles in this is always is an even permutation. So, let pi belongs to the An, then pi can be written as theta 1, theta 2 up to theta 2 r is a product of all the even number of a transposition. So, we take a theta 1 is a 1 transposition, theta 2 is 2, and then up to theta 2 r, then there is a product of an even number of transpositions. So, thus we may write theta can be, pi can be written in the form of theta 1, theta 2, and then last one is a theta 2 r minus 1 up to theta 2 r, or we can write theta 1 2 r and then add a collection in this, a continuation, though both the way we can write into this form. So, this theta can be written into this form. So, now consider the product of a 2 transpositions theta and theta prime. If the 2 transpositions are identical, then the product is a 1. If we have a theta and theta are the same, if we have a 1 2 and 1 2, and then it is equal to identity clearly. So, if the 2 transposition are identical, then the product is equal to 1. Then if they have a one letter in common, say AB and AC, then we have to write the disjoint cycle, and this disjoint cycle is equal to ABC is equal to 3 letters. And now you know that if the 2 transpositions are identical, the product is a 1, and product 1 is a even, always even. And now if there is a 1 elements are common in the both the transpositions, then this have a written as a 1 ABAC, then ABAC is nothing but is equal to is a transportation in the form of a 3 cycles, the 3 cycles is clearly is a even. Now, if no letter is a common, so A, B and C, D, there is a no letter is a common, both are the disjoints, and is disjoint, then when A, B, we can write as the AC, then C, A, C, D, and then this is written as a product of a 2 3 cycles. So, this means again this can, so this means clearly this means if we have a, this is as a 3 cycles, and then if we have all are the no letter common, then again we have to write as a product of a 3 cycles. So this generally we show that pi can be if n is greater than equal to 3. So we have a just say that a n generated by the product of a all the 3 cycles. So this means if we have writing this is a b c, and then we have a clearly generating the all the pi. So in the case of a n is equal to 3, you know that a3 we have to write as a row, as a generated by row is equal to, you have a 1 2 3, and then by this a3 can be is equal to identity row square. So this means is written as a product of a 3 cycles. This is again is a product of a 3 cycles are there. So if we have to just say that, this means generally we can say that pi is a product of a 3 cycles. Now I just closed this permutation section with the problem. This we have to take if 5 has a 24 elements of order 5, 20 elements of order 3, and 15 elements of a order 2, because you know that order of a5 this is so order of we can simply say that order of a5 is equal to factorial 5 by 2, and then you have to just check there is a total number of element. What is this? This is a 5 4 3, this is equal to total number of this, total number you have a 60s are there. So we just said that total size of a5 is equal to 60. So in this 60 he is saying that 24 elements of order 5, 20 elements are order 3, and 15 elements of our order 2. So we have a and of course there is a one is the element of a identity. So you have a clearly one is the even number of identity. So one element clearly. So now we have to write the note that we can decompose any permutation into a product of a disjoint cycle in S5. Since disjoint cycles and we have to prove that if cycles are disjoint, then they are permutations is a commute. So disjoint cycles always commutes. So an element must be one of the form, and we have a, because it's a 5 element, so A, B, C, D, E, that is a only one we have to getting this is a even, and then we have a product of a like this A, B, C and D disjoint cycle, and this is 3 cycle is a even, and this is equal to, you have a true transposition. So odd then is clearly even permutation, odd permutation, this is giving you a odd permutation. And then the third type is this ABC, and this is a 3 cycle, this is always is a even, and you know that the fourth one is a product of these two, and this is again is even, this is odd into odd is equal to even, and the last one is we have a AB, and this is simply is an odd, and then we have a identity element finally is a even permutation. So the elements of this as 5 are disjoint elements have a one of the form. So S5 element of S5 is this one of the 6 forms, but we are interested into 1 and 3, and we have a 4 and 6. So we have a, because the elements of this A5 is a collection of all even permutations. So if it is collection of all even permutation, that means this A5 can be collection of this 1, 3, 4 and 6. We have to discuss this into one by one. So permutation in A5 of the form 1, 3, 4 and 6, as I just say that. So we just say that we know that when a permutation is written as a disjoint cycle, it is order is the least common multiple of the length of the cycle. So if we write two permutations as a disjoint cycles, then we can order of this is clearly we have to take a least common multiples of the length of the cycle. So if we have a three cycle and we have a 5 cycles, these are the permutations. So we have to take a 3 and 5 LCM of this least common multiple of this, then we have to write the order of that cycle. So we have a B, C, D, E has a order 5, and then you can say that if A, B, C, D is a order 5 clearly, and then A, B, C has a order 3, and then this is order 2, and then we have a order 1. So one of the element we have a order 5, we have to show that this is a this types of has a 24 element, this is types is a 12 element 20, and this types of a order 5 has a we have a 24 element, order 3 is a 20 element, order 2 is a 15 element. So one is this, so we have a total is a total number of element in alternating group of A5 is a 60. So we start from the 1, so we have a total A, B, C, D, D, E. So this means the only permutation in A5 has the order 5 of the form 1, this is order 5 key, only this form. So clearly this form means there are factorial 5, because we have a B, C, D, E, then we have 5 choices for A, then we have for B is we have 4 choices, then C is we have 3 choices, is a 2 choices, is a 1 choices. So means there are factorial 5 distinct expression of the cycle of the form of A, B, C, D, E, where all A, B, C, D are distinct. So this means we have clearly 5 choices for A, and then we say that then 4 choices for B, 3 choices for C, and we have 2 choices for D, and 1 choice for E. So this means we have only for E for is only 1 choice, D and 2 choices, C. So we can start the total number of a distinct expression of a cycle of the form is a factorial 5. But however, not all these expressions represent distinct permutation. In particular, there are 5 equivalent notation of any permutation of the form this A, B, C, D, E. Then we have a B, C, D, E, A. Then we have a C, D, E, A, B. Then we have a D, E, B, A, C, and then these all are the same. We have to write in the cyclic notation. So total is a factorial 5, but these 5s are equal. So this means we can excluding these 5s from this the factorial 5. So all are equivalent. These 5s are equivalent, and any other reordering of the symbols is non-equivalent. So we divide the total number of a notation factorial 5 to get the number of a permutation of order 5. So that is we have to just write factorial 5 over 5, then we have a clearly is equal to we have a 24. So total number of elements of order 5 we have as a 24. Similarly, for the case of we have for order 3, there are 20 permutation of order 3 and 5, and then arrangement as very similarly we have A, B, C types. We have to just say that since the only permutation in a 5 of order 3 of the form of A, B, C, so there are 5, 4, 3 different way to write such a cycle, 5 choices, 3 choices, and 2 choices. Then we have 5, 4, 3 choices, then 5, 4 into 3 different way we can write the cyclic notation. But again there is these 3 A, B, C, B, C, A, C, A, B are the equivalent. So we have to must divide this by 3, especially which is different notation represent. So we have to 5, 4, 3 divided by 2, then we have to getting the 20 elements. So that means we can say that the permutation of order 3 in A5 is 20, and then we have to take the order of a 2. So even permutation of order 2 are the little bit trickier to count, because they must of the form of a B and C, D, and so there are the 5, 4, 3, 2 way to write such a permutation. However, since the joint cycles commute, there are 8 different ways to differentially represent the cycle produce the same permutation. These are the 8 way we have to write A, B, C, D, B, A, C, D, and A, B, D, C, B, A. These are because of the disjoint cycles are commute. So, this is total 8 different way we can representing into this form. So, there are we have 5, 4, 3, 2 and divided by this 8. So, we have total is equal to 15 we have to just. So, we have to permutation of order 2 is equal to order 2 in A5 is equal to 15. So, this is the complete the solution of a this problem, but now you see this is the last one. Even for a this order 2 we can easily calculate the number of permutation of order 2 in different way also. However, because we have a total permutations of this an is equal to 60 and A5, then exactly one of these has order 1 and every permutation of A5 has order 5, 3, 2 and 1, and then we have to calculate the 5 and 3. So, once you have know that the 24 permutation of order 5, 20 permutation of order 3 and 1 permutation of order 1, then you know that 60 minus 1 minus 24 is equal to 50. So, there are so there must be 15 permutation of order 2. So, we can calculate this order 2 permutations in this way also. So, this means we can easily calculate the any such types of problems for solving how to write a number of permutations order of a elements of this into the cyclic permutations of this even alternating group. So, I think we have to I have complete the portion of this permutations in this class, and so I just stop here, and in the next class I will start with the coset, and we have to define the cosets and some examples and discuss the property of a coset, and then we move to the Lagrange's theorem, important theorem of a Lagrange's of this course. So, thank you for today.